Hello friends. Now today we'll discuss about the experimental stress analysis. So before starting this particular subject, that is introductory part, we will discuss about one of the subject. That subject is called as a strength of material. Nowadays it is also called as a analysis of mechanical element. Also it is called as a mechanics of material. So whatever the strength of material is there, it is totally based on the theoretical concepts. That means in the strength of material the standard formulas are available. We need to consider some of the standard formulas which we have derived. Also we have to consider some of the assumptions, and based on that particular assumptions we have to obtain the solutions for the different types of the elements. Therefore the subject is also called as a analysis of mechanical elements. There are so many elements are there, that is two-dimensional elements, three-dimensional elements. Also shaft is there, then beam is there, then column is there. All those elements are there, in which we are going to find out their stress analysis, their strain analysis, their deformation analysis. All these parameters we are going to calculate in the strength of the material. But as already we have discussed, that is, while solving such types of the numerical, such types of the problems, we have to consider the standard formula, we have to consider the standard boundary conditions, as well as we have to consider the standard assumptions. Then what is meant by the boundary condition? The boundary condition represents the current position of that particular element. Suppose if I will take the example of the cantilever beam. The cantilever beam is having their own boundary condition, that is, one end is fixed and another end is free. If the cantilever beam will satisfy this condition, then and then only I can use that particular standard formula for the analysis of that particular cantilever beam to find out their shear forces, to find out their bending moment, as well as to find out their slope, to find out their deflection. Second one is the assumptions. Once again I will take the example of the shaft. In the shaft we are going to find out their shear stresses, we are going to find out their angle of twist. But before that, the shaft should satisfy most of the assumptions. In that, the first assumption is the material of the shaft is homogeneous and isotropic. The shaft should be circular, it should be straight before twisting. Such types of the assumptions we have to consider in the strength of material. And if that particular element satisfy all those boundary conditions, satisfy all these particular assumptions, then and then only I can use the standard formula. But as we know that some of the bodies are there which are having the irregular shapes, so for such types of the irregular shapes, such types of the boundary conditions are not applicable, as well as such types of the assumptions are not applicable. Then how such types of the problems will be solved? At that time we have to use one technique, and that technique is called as a experimental stress analysis. That subject is also called as experimental mechanics. Whatever we have discussed about the strength of material, such types of the analysis is called as a TSA, that is theoretical stress analysis. And whatever the results are calculated experimentally, that concept is called as ESA, that is experimental stress analysis, or it is also called as a experimental mechanics. So the experimental stress analysis is one of the standard technique which are mostly used in the industries or in actual applications to find out the results experimentally. There are basically three experimental stress analysis techniques which are used for the stress and strain analysis. Also used to find out the shear stress analysis. It is also used to find out the direction of the principal stresses. Also it is used to find out the standard values of the materials. It is also one of the techniques which is used to find out the different type of parameters, likes to find out the pressure, to find out the strain in rotating shaft. Also it is used to find out the vacuum. Also it is used to find out the torque induced in the rotating shaft. So all the results are calculated experimentally, therefore that concept is called as a experimental stress analysis. But whatever the ESA techniques are there, while calculating the readings or while calculating the results by using the experimental stress analysis, it is not required to consider the body having the regular shapes. It is not required to consider the standard assumptions. Also it is not required to consider the standard boundary conditions. Any type of body or any type of structures can be analyzed by using the experimental stress analysis. So now we are going to discuss about the three important methods which are used in the experimental stress analysis. In that, the first method is called as a photoelasticity, second method is called as a coating method, and the third method is called as a strain gauge techniques. So now we'll discuss about the first techniques, that is the photoelasticity. Now in case of a photoelasticity, the concept of the photoelasticity is applicable for the concept of the photoelasticity is applicable for only for the transparent materials. The transparent materials, in the sense, it is applicable for only transparent materials. That materials are called as a photoelastic materials. But before that, whatever the instrument is used for such types of the transparent material, that is analysis of the transparent materials or the analysis of photoelastic models, that instrument is called as a polariscopic device. So now see, this is the basic construction of the polariscopic device. So towards the left sides, the one light source is there, then after that polarizer is there. At the extreme right side, one analyzer is there, and near to that analyzer, one camera is there. So, and at the center position, one attachment is given. That attachment is called as a loading frame. So whatever the model we are going to analyze, that model is loaded at its center point, and that load may be tensile, that load may be compressive, that load may be bending. As per the requirement, we have to apply that particular load. And as we know that after the application of load, the physical property of that particular material will get changed. So now here the physical properties will get changed, and it has been observed in the form of different types of colors, and that colors are called as a fringes. And it has been observed by using this particular polariscopic device, and whatever the fringes are developed in that particular model, that fringes are used to find out the direction of principal stresses, as well as it is used to find out the magnitude of principal stresses. Then how that polariscopic device works? So simple working principle is there, that is the light source is there, polarizer is there, at the center point the loading frame is there, and then the analyzer is there. So that polarizer and the analyzer are one of the transparent materials. In addition to that, the two elements are also there, that is quarter wave plate 1 and the quarter wave plate 2. So one quarter wave plate 1 is provided before photoelastic model, second quarter wave plate 2 is provided after the photoelastic model. That means your model is in between quarter wave plate 1 and the quarter wave plate 2. Now then what exactly happens related to their working? Now if suppose if I have taken the circular disc, and on that particular circular disc I have applied the compressive load, so due to that compressive load, their physical properties will get changed. At that time, what we have to do, we have to start that particular light source, and whatever the light is emitted from that particular light source, it is passes through the polarizer, it is passes through the quarter wave plate 1, it is passes through the photoelastic model, then it is passes through the quarter wave plate 2, then it is passes through the analyzer, and then that light rays are coming out from that particular analyzer. If that model is in loading condition, its physical properties will get changed, and that change in physical properties will be observed in the form of different types of color patterns. But instead of it is called as a color patterns, it is called as a fringes. It is called as a fringes, and that fringes represents, the change in physical properties of that particular circular disc, and that fringes are used to find out the direction of principal stresses as well as magnitude of principal stresses. Now second, so this is the basic construction of the photoelastic material. So what it indicates, that particular photoelastic material is again made by the casting process, as we have discussed about the casting process and the manufacturing process. That is one molten metal is there, and that molten metal is poured in the particular pattern, and after that we will get that particular casting product. Similarly, photoelastic material also prepared by using the casting process. It can be prepared by using araldite and the hardener. Also it can be prepared by using the epoxy resin. So araldite, if I will take the example of araldite and the hardener, nowadays the araldite and hardeners are easily available in the market. So we have to take the mixture of araldite and hardener in the form of ratio of 100:1 or 10:1. In that particular liquid, I have to pour it in that particular mold, and finally I will get such types of the products. This particular materials is called as a photoelastic material, and whatever the polariscopic device is there, that polariscopic device is used for the analysis of such types of photoelastic materials, that is to find out the direction of principal stresses as well as to find out the magnitude of principal stresses. Then next, as we have discussed about the concept of photoelasticity earlier, we have discussed about the concept of the polariscopic device, how it is used for the stress analysis. So these are the so many examples in which the analysis of photoelastic material is carried out. So in the first figure, one circular disc is there, and that circular disc is under the compression, that means compressive load is applied. So due to that particular compression, so their physical properties will get changed, and that change in physical properties are observed in the form of different types of colors, and that colors are called as a fringes. So here we can observe the different types of color patterns. So these particular color patterns are called as a fringes, and that fringes are used to find out the direction and the magnitude of principal stresses. Why these fringes are visible here? Because this is one of the transparent material. If here, instead of taking that particular photoelastic material, if I will take one metal, or if I will take one metallic disc, and if I will apply the compressive load, and if I will apply the light sources, so light is not transferred from that particular metals, so it is not possible to observe the change in physical properties in the form of color. But here, as this material is one of the transparent material, therefore the light is passes through that particular material, and we can observe that particular change in physical properties in the form of different types of colors. Similarly, in the second figure, the triangular sections are there. In the triangular sections, they are subjected to the loading, and due to that loading, again their physical properties will get changed, and that change in physical properties are observed in the form of different types of fringes. In the third figure also, we can observe the different types of the fringe patterns. Whatever the fringes are developed, that fringes are developed at the top side and the bottom side, because the load is applied from that particular point, therefore the fringes are developed at that point. And as you know that the load is directly proportional to the fringes. That means if we are increasing the load, the number of fringes are increases. If we are decreasing the load, the number of fringes are goes on decreasing. The number of fringes are goes on decreasing, and both are directly proportional to the each other. Then second, again, in the second figure also, you can see there are different types of the fringe patterns in the circular disc, but there is a basic difference between the types of fringes. There are basically two types of fringes. One is the isoclinic, another is the isochromatic fringes. These fringes are developed as per the requirement of unknown parameters. That means if we have to calculate the direction of principal stresses, then we have to use the isoclinic fringe pattern. If we have to find out the magnitude of principal stresses, then we have to use the isochromatic fringe pattern. So this is the basic difference between the isoclinics and isochromatics, but we'll discuss that isoclinic fringe pattern and isochromatic fringe pattern in detail in the chapter number 2. Now only we are focusing on the concept of photoelasticity and basic introduction related to the ESA. So these are again the different types of figures, that is figures of the circular disc, in which the changing in physical properties are observed in the form of different types of color patterns. Again, these are the some another examples. That is, one hook is there. So when we are going to lift any load, the maximum stress concentration is taking place at this particular point. So due to that stress concentration, the fringes are also developed from the that particular point. In the second figure, that is tensile specimen. If the tensile specimen is under the tensile loading condition, at the center point there is a maximum stress concentration is there, therefore the fringes are also developed from the center point. Now second, that is again, this is the basic construction of the polariscopic device. Now we'll discuss about the second method, that is coating method. But before that, as you know that the basic disadvantages of the photoelastic method, that is that photoelasticity concept is applicable only for the transparent materials, because the light is passes through the transparent material, and through that particular light I can observe the change in physical properties in the form of different types of colors, and that fringes, that colors are used to find out the direction of principal stresses and the magnitude of principal stresses. Also it is used to find out the maximum shear stress and the material fringe value. And that photoelasticity method is called as a quantitative method. Why it is called as a quantitative method? Because the final result is obtained in the form of quantity, that is sigma 1 is equal to 25 newton per mm square, sigma 2 is equal to 50 newton per mm square, tau max is equal to 35 newton per mm square. Like that we'll get the final result in the form of quantity. Therefore the photoelasticity is called as a quantitative method. Now the second ESC technique, that technique is called as a coating method. So that coating method is called as a qualitative method, because in this method you will not get the result in the form of quantity, you will get the result in the form of quality. That means by observing the quality of figure, by observing the quality of crack patterns, we have to decide that is whether stress is low, medium or high. So if you go through the basic construction, so in the first figure it represents the basic construction of the coating method, that is one testing material is there. On that particular testing material we have to apply the layer of coating material, because the coating method, in case of a coating method we have to use one coating material. Through that coating material we have to go for the stress analysis, and such types of the analysis are called are carried out by using one device. That device is called as a reflection polariscope. Again in the reflection polariscope, same elements are there, that is extreme left side light source is there, then polarizer is there, then quarter wave plate is there, then another quarter wave plate is there, then analyzer is there, and then image recorder is there. So the coating method, in case of a coating method, what exactly we have to do, what are the component we have to test, on that particular component we have to apply the layer of coating, and that layer of coating should having thickness near about 5 to 10 5 to 10 mm, or maybe it is near about the 0.5 centimeter or the 1 centimeter, and that liquid or that particular material is called as a brittle liquor. So whatever the material we have to test, on that particular material we have to apply the layer of coating. That material may be stationary, that material may be in rotating condition. If that again we have to apply the light on that particular layer of coating, and that light sources are strikes on that particular test specimen, and again they are reflected from that particular test specimen, and they are moving towards the image recorder through various types of the elements. Suppose now if that particular component test specimen is in moving condition, so due to that moving condition, due to that loading condition, some of the stresses are developed in that particular material. So whatever the stresses are developed, that stresses are transferred to the layer of coating, that stresses are transferred to the layer of coating, and due to that particular stresses the different types of crack patterns are produced in the coating material. If the cracks are produced in only one direction, the stress level is low. If the cracks are produced in both direction, that is in the direction of x and in the direction of y, then we can say that the stress level is medium. But if the cracks are produced in irregular manner, at that time we can say that the stress level is very high. Means we can say that here you will not get the quantity. By observing the quality of that particular crack pattern, we have to decide that is the stress level is low, medium or high. Therefore this method is called as a qualitative method. So this method is not mostly used because it is not a sensitive method, but it is used for the heavy duty applications. For example, if we have to go for the analysis of pressure vessel, if we have to go for the analysis of wind turbine blades, in such types of the analysis this particular coating methods are used. Then in the second figure we can observe that different types of cracks are produced in the number of direction, but the crack level is very less. In the second figure also you can say that the cracks are produced due to the application of load, and by observing this particular crack patterns we have to decide that whether stress is low, medium or Hi, this is about the coating method. This is the instrument which is used for the which is used in the coating method, that is reflection polariscope. In the second figure we can observe that if the light is coming out from the light source, it is coming out from the polarizer, it is coming out from the quarter wave plate 1, then it is strikes on the test specimen, and from that test specimen the light is reflected towards the observer, and that observer has to observe in which direction the cracks are produced, and according to the direction of cracks we have to decide that whether stress induced in that particular stress specimen is low, medium or high. Now we'll discuss about the third method, that is strain gauge technique. As we have discussed, that is the photoelasticity is applicable only for the transparent material. The second technique, coating method, it is not a sensitive method, it is the qualitative method. But whatever the third technique is there, that third technique is called as a strain gauge technique, and this technique is mostly used in the industries for the stress or the strain analysis. As we know that the basic working principle of the strain gauge, that is change in resistance is directly proportional to the unknown parameter. Change in resistance means whatever the strain gauge is there, it is having the standard resistance of 350 ohm, 1000 ohm, etc. 1000 ohm, etc. So if that strain gauge is comes in contact with the any moving parts, its resistance will get changed. For example, from 350 it becomes 450, from 1000 it becomes 1200. So whatever that change in resistance value is there, that change in resistance value is calibrated in terms of unknown parameter. Means if we have to calculate the strain, change in resistance is calibrated in the form of strain. If you have to calculate the stress, the change in resistance is calibrated in the form of stress. If you have to calculate the pressure, if you have to calculate the load, if you have to calculate the torque, that all these parameters will be calibrated from that particular resistance value. So the basic working principle of the strain gauge, already I have told that the change in resistance is directly proportional to the unknown parameters. And as we know that in the tensile condition, resistance is increases, in compressive condition resistance is decreases, and this is the basic working principle on which your strain gauge works. Basically there are two types of strain gauges. One is the metallic type of strain gauges and another is a non-metallic. The non-metallic is also called as a semiconductor type of strain gauges. The metallic strain gauges we have to use in the various types of the static and the dynamic application, but there should not be any temperature content, there should not be any water content, because if the metallic type of strain gauge it comes in contact with the temperature, its resistance will get changed. If the metallic strain gauge is comes in contact with the water, its resistance will get changed, as well as the corrosion resistance of that particular strain gauge is taking place. Therefore the care should be taken. The metallic type of strain gauges should not be in contact with the temperature and the water. But if we have to use the strain gauges in the water applications, at that time we have to use the non-metallic type of strain gauges, or we have to use the semiconductor type of strain gauges in the water applications. So as we go through the figure, in the first figure the basic construction of the strain gauge is there. That yellowish part, it represents the backing material, or it is also called as a thin paper, and at that center portion whatever the that element is there, that element is called as a grid element or the sensitive element. That element is called as grid element or the sensitive element, whose resistance will get changed. But while pasting that particular strain gauge on the specimen, there should not be direct contact between the sensitive element and the test specimen. If there is a direct contact, the resistance immediately it will get changed and it creates the error during the measurement. Therefore, to avoid that condition, one thin paper is there. The thin paper is provided at the top of grid element, another thin paper is provided at the bottom of the grid element. Therefore, due to that condition, there is no direct contact between the grid element and the specimen. So due to that uh, there is no direct contact between the test specimen and the grid element, as well as due to the thin papers, that sensitive elements on the strain gauge is protected from the environmental conditions, and due to that particular thin paper, we can handle that particular strain gauge very easily. So this is basic working principle and construction of the strain gauge. In the third figure we can say that one cantilever beam is there, one strain gauge is pasted at the top side, another strain gauge is pasted at the bottom side. That means the strain gauge 1 is subjected to the tension, and strain gauge 2 it is subjected to the compression. And means in the first strain gauge resistance is increases, which will be calibrated in terms of unknown parameter. In the second strain gauge the resistance is decreases, which will be calibrated in terms of unknown parameters. So these are the three techniques, that is photoelasticity, coating method, and the strain gauge techniques, which are related to the ESA techniques. And as compared in comparison with this particular three techniques, as we have discussed, that is the concept of photoelasticity is applicable only for the transparent materials, or it is applicable only for the photoelastic materials, which will be analyzed by using either plane polariscopic device or the reflection polariscopic device, which is also called as a quantitative method. Then second method we have discussed about the coating methods. That method is called as a qualitative method, in which the final result is obtained in the form of different types of crack patterns. Means by observing the different types of cracks we have to decide whether stress is low, medium or high. And then we have discussed about the third technique, that is strain gauge techniques, which is also called as a quantitative method, in which the strain gauge is used for the stress strain analysis, which works on one principle, that is change in resistance is directly proportional to the unknown parameters. So these are the three basic ESA techniques which are used for the stress analysis. Then we'll discuss about the different types of the light sources which are used in the concept of photoelasticity, as the light source plays very important role in the photoelasticity. So basically there are two types of light sources. One is the ordinary light, which is also called as a natural light, which is also called as a white light. And the second light source is there, that light source is called as a monochromatic light. One by one we'll discuss about the uh, basic properties of the all the light sources. So ordinary light, it is also called as a white light, the light which is emitted from the tungsten filament bulb, mercury lamp, sun rays. Such types of the light sources are called as a ordinary light, and it is having the three important properties, that is it is having the different colors, different frequencies, and the different wavelengths. Whatever the light sources are available in our home, that is tube lights is there, then that tungsten filament bulb is there, then sun rays are there. All these light sources are comes under the category of ordinary light, or it is also called as a natural light, or it is also called as a white light, because it is having the different colors. If such types of light sources are transferred through any particular transparent material, we can observe that different types of colors, because this light is having their own property, that is it is having the different types of colors. Then second light source is there, that is monochromatic light. The light is emitted from the high pressure mercury vapor lamp. This particular light source is called as a monochromatic light. It is having only one color, one frequency, and one wavelength. And mostly in the polariscopic device, this monochromatic light source is used for the stress analysis, because through this particular light source analysis is very simple. Such types of the light sources are used in regular applications also. Previously such types of light sources are used on the roads. As we know that on the roads there are different types of the yellowish bulbs are there, dark yellowish bulbs. That yellowish bulbs represents the monochromatic light sources, and this particular monochromatic light source is used for the stress analysis in the polariscopic device. So what is the basic difference between the ordinary light and the monochromatic light? That is, in the ordinary light, which is emitted from the tungsten filament bulb or from the sun rays, the monochromatic light is emitted from the high pressure mercury vapor lamp. The ordinary light is having the different colors, different frequencies, different wavelength, while the monochromatic light source is having only one color, one frequency, and only one wavelength. And as compared to the ordinary light, the monochromatic light source is used for the strain, for the photoelastic material in the polariscopic device because analysis is very simple through that particular monochromatic light sources. Then polarization of the light, as we have discussed about the one important element in the polariscopic device, that element is called as a polarizer. Because what happens when the light is emitted from the light source, it is having the infinite number of direction. That means some of the light sources are moving in vertical direction, some of the light sources are moving in the horizontal direction, some of the light sources are moving in the back direction, some of the light sources are moving in the inclined direction. But what is the requirement of the polariscopic device? When the light is passes through the photoelastic model, it will be passed in only one direction, that is in the form of simple harmonic motion. That means the light sources are perfectly in the horizontal direction. Therefore, that polarizer is provided after the light sources and before the photoelastic model. That means if the light is emitted from the light source, initially it is having the infinite number of the direction, but if the same light sources are passes through the polarizer, that light is converted in only one direction. That means it will move imperfectly in only one direction in the form of simple harmonic motion. If light is moving in only one direction, then and then only analysis is possible, and then and then only we can observe the different types of fringes in the photoelastic model. And therefore, whatever the light is coming out from the polarizer, that light is called as a polarized light. So before polarizer, the light will be considered as a ordinary light. After the polarizer, the light will be considered as a polarized light. So now we'll discuss about the concept of natural birefringence and the artificial birefringence. So natural birefringence and artificial birefringence, as we know that if the light is emitted from the light source, it travels with some of the velocity, and whatever the working medium is there, that working medium will be considered as a air. So if the light is emitted, the light is passes through the air, so its speed is different. After a few times, if the same light sources are enters into any transparent materials, its speed or its velocity is goes on decreasing, because the working medium will get changed from air to the transparent material. So due to that working medium change, the velocity is either increases or either decreases, and this is the concept on which your natural birefringence and artificial birefringence effects. Okay, so natural and artificial birefringence means there are basically two types of materials, natural birefringence, which are permanently double refractive. That means if the single light ray is enters on that particular natural birefringence material, that light vector is divided in that single light vector is divided into the two vectors. Therefore, this is called as a natural birefringence. That means without application of load, the single light vector is divided into the two vectors. So this is called as a natural birefringence. And what is meant by the artificial birefringence? Artificial birefringence means, you can take the example of glass or the plastic material. If these two materials are subjected to the loading, then and then only the single light vector is divided into the two vectors. If these two materials are in unloading condition, again it will be behaves like a single reflector. That means if the single light ray is enters on this particular material, as it is, that single light vector is coming out from that particular model. But if the same model is in loading condition, if the same model is in loading condition, again the single light vector is divided into the two different vectors. Therefore, this is called as a double refractive material. So what is meant by the single refractive and double refractive? Single refractive means without application of load, if the light is divided into the two vectors, such types of the materials are comes under the category of natural birefringence material. And natural birefringence material, and if without application of load, if the light vector is coming out as it is, it will not be divided into the two vectors, it will becomes under the category of artificial birefringence material. So these are the basic types of material, that is natural and the artificial birefringence. So this is about the basic about the experimental stress analysis, in which we have discussed about the basic use of the ESA techniques. Then we have discussed about the three methods, that is photoelasticity, coating method and the strain gauge techniques in details, how these methods are useful for the stress analysis and how it is applicable for the different types of materials. And also we have discussed a lot about the types of light sources which are used in the polariscopic device. Now in the second part we'll discuss about the detailed working principle of the polariscopic device, that is how the polariscope is used to find out the direction of principal stresses and the magnitude of principal stresses. Thank you.